Hello, and welcome to the Magical Mystery Tour, a roundup of observability data stores. So I'd like to start with a little quote. This is from Patrick McFadden when he was talking about the next 10 years of Cassandra at Apache Con. A developer will never ask you, hey, what file system is that? So just to start off, I'd like to thank you all for being here and for joining this talk. You are part of the special few who actually care about things like file systems and the nitty-gritty of how your databases actually work under the hood, which is what we're going to dive into in this talk. So quickly, an introduction. My name is Josh Lee. I am an open source advocate at Altinity. We do hosting and support for ClickHouse, which you're going to hear me talk about a little bit in this presentation. An important point of clarification, ClickHouse is a registered trademark of ClickHouse Incorporated, and Altinity is not affiliated or associated with ClickHouse Incorporated, but we are open source contributors, and we are huge fans of the project. So first, a definition, right? We're going to be talking about observability. There are lots of different definitions of observability floating around out there. I like to simplify it down to this equation, right? Visibility plus understanding equals observability. So really that just means, do we have enough information coming out of the system that we can see what the system is doing? And do we have enough context about that information that we can understand it and maybe change it if we need to? Now, that sounds simple, but it actually kind of comes at a huge cost. So I mentioned data, right? We need enough data that we can see what's happening and that we can understand the context. It actually turns out that's a lot of data. This is just a rough rule of thumb that I use. Of course, it's going to vary depending on the shape of the problem that you're solving and the shape of your system. But as a rough rule of thumb, you're going to have 1 to 2 orders of magnitude, or about 50 times more observability data than you will have like system record data for your transactional system. So we're talking about huge volumes of data that we need to keep somewhere. And this is really the challenge of modern observability, especially as that core system data itself is expanding exponentially, right? Our observability data sets are expanding even faster, creating significant challenges for the architectures of your. So what are we actually storing when we talk about observability data? Well, first of all, we have the signals themselves, right? Of course, that's going to be the bulk of our data. These days, if we're looking at open telemetry, that's going to be metrics, traces, logs, profiles, and events. If we're thinking in sort of more of an observability 3.0 way, we might just be thinking about all of these things as different shapes of events. All of those things are going to be sorted and organized based on labels and tags, which is sort of the most basic and elementary way to find and organize these things. In OpenTelemetry, that evolves a little bit, and we have this concept of resource metadata, which is a set of key value pairs following the OpenTelemetry semantic conventions that precisely describes the entities, right, the resources. So that's things like virtual machines, pods, hosts, containers, processes, right, all of the sort of dependencies that a service might be running in. The service itself is a resource, right? So we have metadata that allows us to identify those things and group the telemetry signals around those things, which is an extremely useful way to look at it, and a little bit more robust than just simple labels and tags. Then once we kind of have that map of those different entities, those different resources, we can start to draw dependencies between them, which lends to graphs and topologies, which we can also get in intra-service topology from our distributed tracing. These can be another really useful way to navigate those core signals, right? So this is a useful thing to store. They can be expensive to calculate, and topology is sort of a snapshot in time. So we're probably going to be storing something that looks like a snapshot, and if we've got snapshots, we'll probably introduce something that looks like a delta. And then finally, right, we need all of our configuration data. So this is stuff like alerts, users, configurable dashboards, and so on, that might actually belong in a transactional database. So I said transactional database. That's one type of database. There's also an analytics database. We're going to talk about the differences in a little bit. But first, there's a few more things that we need when we're thinking about an observability data store solution, right? So the first most important thing we need is fast streaming rates. We need to be able to keep up with the ingestion of all of the data being emitted by our system. In the worst case scenario, if the database receiving the writes is unable to receive the writes, you could actually crash the system being monitored. You really want to avoid this. You should architect your system so that doesn't happen, and instead you're just dropping data in the case that your database can't keep up. But even dropping data is not ideal, so we want to make sure that our database can keep up. As I mentioned before, right, this is a huge amount of data, so we need some kind of efficient compression and storage to minimize the cost of storing all of it. We're going to probably only care about this data for a certain amount of time, usually about 2 weeks. We're definitely going to care about the last 24 hours worth of data and even the last hour's worth of data much more than any of the older data. So having some kind of time-oriented management that allows us to manage those retention policies and potentially roll-up and TTL and hierarchy strategies is going to be important. And then we need real-time analytics. So I kind of hate this because it's a buzzword, and I hate buzzwords, but it is a really useful word that I don't have another way to describe what this is describing, right? So we don't literally mean real-time. That's why we've got the scare quotes. Anyone in marketing who tells you they're selling you real-time analytics, they don't really mean real-time, of course, right? We're not being pedantic about this. What they mean by real-time, though, is that it's in the order of seconds. It's something where a human pushing the button can see the response instantly without getting antsy. So that's like 1 to 2 seconds versus, 20 seconds, minutes, hours, or even days that we might be used to with some of these large ETL pipelines and things like that. So what is real-time analytics? Well, anything you can do with a group by, that's what analytics is. Thanks to Peter Marshall from Imply for this excellent quote describing what analytics is. That group by, though, that implies that we're actually aggregating analytics across multiple rows, right? So what we really need for observability when we're talking about real-time analytics is the ability to aggregate across multiple rows really, really quickly, and calculate sums, P99s, averages, things like that across potentially billions of rows. Sometimes we don't know exactly which rows we're interested in, so especially for logging, full text search can be really, really useful. If we're being organized about our tags and labels and resource metadata, then we can use those as indexes and as a way to find the specific telemetry signal data that we care about. In the case of alerting, right, we really only care about the last data point and if it falls inside or outside of an expected range, so that we can fire an alert if it's outside of the expected range. So for alerting, we have a lot of really, really fast reads of that last data point. And then observability data that we've talked about so far doesn't really get updated, right? We are writing it to our storage and then reading it many, many times, like especially in the case of alerting, as we've just discussed, but we're not really updating it or changing it. So we don't need the things that a database would have that would allow us to guarantee changes or updates to our data that can be expensive and can slow down that really, really fast ingest that we do need so badly. So let's talk about the different database archetypes. I kind of hinted at this earlier, right? So we have OLTP. This is an online transaction processing database. These are the typical databases that we're all familiar with, MySQL, Postgres, and so on. And these are great for actually storing anything where we need it to be a consistent view of the world everywhere. So anything like accounting, actual transactions, right, user interactions or user feedback, or things where you are going to be concerned about individual rows and you want them to be accurate. An OLAP, or an online analytics processing database, gives up some of those guarantees of consistency and accuracy in exchange for speed, right? So OLAP databases are really oriented around being able to read and write data very, very quickly, and we'll talk about some of the architectural tricks that make that possible. Then in the space of observability, we have some custom-built databases specifically for time series. So Prometheus would be the most famous of these, but there are other databases that sort of share this architecture. We'll talk about this time series DB architecture. And then we have databases that have more of a search and analytics architecture. All of these kind of tend to bleed into each other, and no database these days actually fits neatly into one of these categories. So I can't like go through these categories and talk about the databases that neatly fit into each one. Instead, we're going to kind of talk about the characteristics of these types of databases and how some of those characteristics are shared by some of the actual databases that we could choose for our systems. Okay, so what are those databases that we could actually choose for our systems? Well, of course, we mentioned Postgres. We're going to talk about that a little bit as sort of a frame of reference for how a transactional database works and how these other database architectures are a little bit different. Cassandra is an OLTP database that's commonly used in observability, especially for logging. It maintains some of those transactional guarantees that Postgres has, but also has a little bit of a speed up and some more horizontal scaling tricks up its sleeve. We've got OpenSearch and Elasticsearch and that whole family of databases, which is really, really great for full text search, semantic search, things like that, and can also leverage powerful analytics features. As I mentioned, we have got Prometheus and the family of time series databases, and then ClickHouse is sort of the archetype of an online analytics processing database that we'll be looking at, although there are, of course, others. So just to kind of map these out, right, I said none of these really neatly fits into their category perfectly, but here's sort of how I would arrange them on a graph of those different types of databases. Okay, so when we're talking about databases, the most expensive thing is the actual reading and writing of data to the disk. If we can minimize the amount of data that needs to be read from the disk, we can dramatically speed up our queries. And the faster that we can write our data to the disk, right, the faster that we can be available for further inserts. So the way that the data actually gets stored on the disk can be really important for the actual performance characteristics of the database. And there are a couple of different strategies for how we can store the data on the disk. We have heap pages plus the commit log. I'm going to talk about how those work. We have append-only time series blocks, and then we have immutable parts and segments, and we'll talk about each one of these. So heap pages are really oriented around trying to keep the space that the database is taking up compact and fitting into a specific part of the disk. I like to think of it as kind of like a JBOD of storage styles, because we're not really concerned with organizing the data in a way that's efficient to read. We're just kind of packing it in and making sure we have somewhere for everything. So kind of how heap pages work is we would have like these pages. Each page contains typically rows, but it could also be documents in the case of a document-oriented database. And then say we mark one page for deletion. Well, then there's this process called vacuuming, or there are other names for it depending on the database. But there's some process of cleanup that will remove those pages that were marked for deletion. We then have some space available on our disk. And the next time there are some new inserts, that new page gets inserted into the first available slot, keeping everything nice and compact. Then we have time series database blocks. These are append only. So basically what we have is we have a file, one for each individual time series. Any unique combination of labels is a time series. And then we simply record our samples into that file. So this is very straightforward architecturally, but it also has the benefit of keeping everything laid out for one time series in one place, which makes it nice and easy to read later, as we'll kind of talk about. Then we have immutable parts or segments with a background compaction process. So this builds on the append-only nature of the time series database, but adds this background compaction so that we're further optimizing the storage and the ordering of the data so that it can be read even faster. So what that looks like is we have batch inserts, which create new parts or partitions, or in some databases, they're called segments, right? And those segments are then merged in the background with existing data into larger and larger parts that can be then read more efficiently because all of the data is laid out in a nice ordered fashion. So how do we actually write the data? Well, most of these databases are buffering the writes in memory in some way. And then, of course, we have to actually lay the data out on the disk in the correct format, which can take time and doesn't necessarily happen immediately. And there can also be issues of the actual block object caching at the operating system level. So we don't necessarily want to rely on that. We need something more durable, and that's where write-ahead log or commit log comes in, where basically we very quickly commit all of the queries themselves to disk, not the actual data generated by the query, but the query itself and the metadata about it. And then if something ever happens to the data on the disk because the server was rebooted or the process crashed or something like that, we can simply go to the write-ahead log and replay those queries, recreating the data that they would have created. And then, well, we have multiple readers and writers, right? We have multiple processes accessing a database at the same time, and we need some kind of way to give them a consistent view of the world. There are a couple of different strategies for doing that. These are just some of them. So the first would be multi-view concurrency control with that vacuuming process that we mentioned earlier. And the way that this essentially works is that when we write new data, we create a new index. And so anytime there's a process reading data, it has a specific index, and we're basically creating new snapshots as the data gets updated so that each process can have its own snapshot of the state of the world at the time that it is querying. Then we have a strategy called tombstone deletes. This is very straightforward. We simply mark certain sections of the database as deleted, and then when readers are accessing the database, they check the tombstone files to see which data they should ignore. And then finally, we have last write wins, which is just as it sounds like. Everything is just writing data, and whichever write was last is the one that will be regarded as canonical. We need some way to actually keep track of this data that we're writing. So this is where indexes come in, and the most basic and sort of first initial type of index would be the balanced tree index. So this is actually what Postgres uses, and it's a way of keeping track of where on the disk certain rows are. So now we have enough information to actually build a full Postgres, right? We have all of the architectural components that make up a Postgres. We have the write-ahead log, we have heap pages with multi-view concurrency control, and we have balanced tree indexes. This is pretty great. It gives us those ACID guarantees that we need for a transactional database. It's very nicely optimized for updates and upserts and row-level reads, which are the types of use cases that we'd be using one of these databases for. But scaling horizontally is very, very challenging. We don't have those dramatically fast ingest rates that we need for observability, and we don't have the ability to do analytics over billions of rows like we need for observability. So we need something a little bit more purpose-built, right? The first architecture I want to talk about is the analytics and search architecture. So as one example of this architecture, we have log structured merge tree. And this is a strategy for storing data on disk and in memory. It's actually used by Kafka as well as by the Lucene engine, which is used by OpenSearch and Elasticsearch and a number of other databases. So the way that log structured merge tree works, and this is a great diagram I shamelessly took from Ben Stopford's blog. I highly recommend checking out his blog. He explains this stuff way better than I could. But basically we have data coming in this case in key value pairs, being sorted and buffered into disk and then flushed to these small sorted files. These are those immutable segments that I was talking about earlier. Right, so then once we have those sorted files, we then have a background process that merges and compacts them. As I mentioned, this is how the Lucene engine works, which powers Cassandra, Elastic and OpenSearch, and also Apache Solr. So very popular engine that you may have used without even realizing it. It also includes a query language, so you may have used this query language in your observability tool, especially for log search. This is just a basic Lucene query. And then we have Cassandra. So Cassandra doesn't actually use Lucene or SQL, it uses CQL, which is sort of an extension of SQL. And Cassandra gives us a lot of the benefits of an OLAP, but in something more Postgres shaped. So I'd like to think of it as like a wide event, scalable transactional database, which can be a good starting point as we're starting to scale up to these observability shaped workloads. And then we need something more than just really, really fast reading and writing, right? We need a way to actually find the data that we care about. And this is where vector engines and search architectures come into play. So we have a couple of tricks that we can use to make this data easier to find. Most of them come down to how we actually index the data. So inverted indexes, Bloom filters, approximate nearest neighbor, and then also sparse indexes. And we'll talk about each one of those. So an inverted index, pretty straightforward. Basically, we're inverting the way that a typical index works, where we have a pointer that is pointing to some data. We flip that around and we now have some piece of that data, usually an n-gram or a word or something like that. And that then points to all of the pointers that contain the point to the document that contains that word or that n-gram. So in this way, we could really easily build like some kind of literal search engine if we wanted to find all of the documents that contained exactly the word dog or the word parrot. Bloom filters combine sort of an inverted index concept with a little bit of math. And instead of storing the literal n-grams themselves, we hash all of the n-grams, which allows us to have a slightly more compact index that doesn't take up quite so much disk space because we're not creating an index for every single word in the English language. But instead we have a smaller subset of hashes. And with these hashes, we can't tell for certain that a word does appear in a certain document, but we can tell for certain if it doesn't appear, which then allows us to skip that segment of the disk when we're doing our read. And as we've mentioned, any segments of the disk that we can skip, that's a huge benefit. That's going to dramatically speed things up. So Bloom filters can be really powerful. There are other types of skip indexes where you do things like calculate the min-max value or the sum or other types of calculations based on the data in a column or in a document, and then use that in order to identify sections of the data that you may care about for a specific query. Those are useful for finding literal strings, but often we want semantic search, where we're finding words that are related even if they don't actually share the same characters. And the way that we do this is we store each word as a vector, right, which can be sort of a multi-dimensional representation of the word's meaning. And if we're storing all of the words as vectors, well, we don't necessarily have relationships between them the way that we would in a relational database. But since they're plotted in a multi-dimensional space, we can start to draw relationships between the nearest neighbors. And using that tree, that graph of all of the nearest neighbors, we can form an index that can allow us to quickly search and find the specific meaning that we're looking for. So this is a very basic diagram of an approximate nearest neighbor graph, and we would have multiple layers. So the bottom layer would actually contain all of the documents and words for all of the documents graphed to each other, and then we create sparser and sparser indexes on top of that that allow us to quickly navigate to the section of that large world index that we want to get to. Okay, so that's really cool, and that would allow us to build a semantic search engine. But what if we just want to deal with that that last sample issue, right? What if we have alerting, or we want to draw some pretty graphs in Grafana or Perses? Well, that's where we're going to deal with time series and metrics, and Prometheus is sort of the canonical example of how a metrics database should work, and is also the canonical example of a metrics database. Right, so we kind of showed this before. How it works is we have these append-only files, one for each time series, and we're appending the last sample. This is great in theory, but in practice it means we do have to think about our labels quite a bit, because the number of a unique time series that we're going to have sort of follows this formula of cardinality to the power of dimensionality, which means introducing a new dimension can be extremely expensive, introducing higher cardinality dimension can be very, very expensive, and if your observability vendor charges you on the number of unique time series, that's going to be literally financially expensive, and if you're running Prometheus self-hosted or something like that, it's going to be so computationally expensive that it could knock it over. So this is certainly something to watch out for when we're using time series databases. We end up with, like I mentioned, one time series for each unique combination of labels, meaning we really have to think about whether it's worth keeping something as a label or not. There is one really nice benefit of keeping the data laid out in this format, though. It's that we already have all of the data we care about for most queries next to all of the other data for that query on the disk. So we think about a typical database like Postgres, it's storing rows, which means when we want to read an entire row, it's very easy, all the data is right there. But if we wanted to read all of the columns in a single row, we actually have to read, or if we wanted to read one column across all of the rows, we actually have to read each row in its entirety. And another side effect of storing the data in that way is that we have multiple different types of data next to each other, which means we can't really compress it very easily, if at all. If we flip that and we actually store just columns, where the place in the column is indexed to a specific row, then we end up with data structures that are all a single type and can be very, very easily compressed. And when we want to do a calculation across a single column, all of that data is already right there ready for us to read very, very quickly. As a quick example of what that can mean, say we have a database with 109 columns and it's 59 gigabytes worth of data. If we wanted to read across 3 columns, if we wanted to do an aggregation across 3 columns across all of the rows for that database, in a row-oriented database, we would need to read the whole database. We'd need to scan 59 gigabytes from disk. In a basic column-oriented database, we're down to less than 3% of that data, so we'd only need to read 1.7 gigabytes from disk. But because that data can be compressed so much more easily, it actually ends up being less than 0.5% of that original 59 gigabytes. And then because of the fact that we can run this in multiple threads or even on multiple nodes across multiple disks, we can speed that up even faster and get the total read down to 2.6 megabytes from that original 59 gigabytes. So that's really, really cool. What if there were a database that did that? Well, that's where ClickHouse comes in. So ClickHouse is a column-oriented database, and it uses a merge tree engine under the hood, which is similar to the log-structured merge tree, except in this case, instead of storing key value pairs, we're storing columns. And as these fully merged parts grow, we end up with larger and larger blocks of data from the same column that can be very easily scanned and read and calculated. ClickHouse also introduces a concept called sparse indexes. So unlike inverted indexes and plume filters, which can be somewhat dense relative to the data that they are indexing, a sparse index really just contains 2 pointers on an ordered key. Typically, this is going to be date, and says this segment of the disk contains all of the rows between this value and this value. So it allows us to really, really quickly and cheaply find large segments of data that we care about for a query. When combined with skip indexes, this can lead to really, really fast queries. Okay, so to wrap things up, I'm just going to quickly talk about sort of which database you should choose for which use cases. And this is a diagram that I use in some of my presentations. I love all of these choices. These are all great choices. This diagram specifically comes from some stuff that I'm running in my home lab. If you were to pick just a single database for just a single telemetry signal, these are probably the ones that I would choose. ClickHouse for traces, Prometheus or something compatible for metrics, and something like OpenSearch for logs. But that's too simple of an example, an answer for everyone. So let's talk about some more specific things. One database that I didn't really mention at all, but that is has a great architecture is VictoriaMetrics. So we actually use this under the hood in attendee.cloud. And the way that it works is it kind of combines that time series database format that Prometheus uses with a background compaction and optimization process that makes the data much more compact on disk, which, as we've talked about, can also make your queries much, much faster. So VictoriaMetrics is a great choice. Loki actually shares similar architectural choices to Prometheus with sort of an append-only structure. It does not maintain full-text search indexes, so if you want to do full-text search with Loki, you do have to scan all of the logs that are stored inside of it. But it is very simple architecture, very simple and easy to deploy. We also use this inside attendee.cloud, and it does also have really good indexing of the labels, so if you are organized about your labels, it can be a great tool to quickly hone in on the logs that you care about. And then some honorable mentions for some other databases that we didn't have time for. Cortex, Thanos, and from the Linux Foundation, Mimir from Grafana. TimescaleDB is an extension for Postgres that makes it suitable for time series. Apache Solr, Apache Druid, these are all great choices. So some more recommendations. At very small scale, I would say just use what you have until it breaks. That might mean using Postgres with extensions if you're already using Postgres for your LTP. If you really, really need full text search, then OpenSearch is simply the best choice. It's got all of the features you will need. If you want to use just one database for everything, for all of your signals, you can check out my talk on YouTube about this, but I think ClickHouse is pretty cool. And if you are looking at doing wide event analytics, then ClickHouse is simply awesome. If you need to heavily filter your data before you do your analytics on it, then OpenSearch or Elasticsearch can be a good choice here. And as we've talked about, if you need to do lots of those last sample reads and you are looking at an alerting use case, then a time series database like Prometheus or VictoriaMetrics is going to work very nicely. And then finally, not strictly observability focused, but if you do have some kind of transactional or business insights data that you want to combine with your analytics or your observability data, then you could look at something like Cassandra, or you could use something like the sync connector for Postgres and take your transactional database and dump it into your analytics database so that you can maintain sort of the benefits of both and get those high-speed analytics on your transactions. So I will leave you with this kind of overview of the databases that we've talked about and some of their properties. As I've kind of mentioned, all of these databases have been really borrowing tricks from each other. So most of them can be used for most purposes in a pinch, but they're all going to have their areas to shine. And I hope I've kind of highlighted that here and that this talk was useful. That's all I've got. Thank you so much and happy querying.